Good afternoon, everyone, and welcome to the second webinar of 2023-2024 EMOS Webinars program. My name is Francesco Schiripa, and I'm a researcher in statistics at the University of Pisa in Italy. As member of the EMOS team of my university, I'm working at the organization of this webinar program on behalf of Eurostat, together with the German company Statistical. Today, I act as webinar moderator. Now let me first explain for any newcomers that EMOS stands for the European Master in Official Statistics, a joint project of universities and data producers in the EU member states, EFTA and EU candidate countries. If your university is interested in applying for the EMOS label, please consider that a permanent open call for universities is available on the EMOS dedicated page on the Eurostat website. For staying in contact with the EMOS news and communities, please follow the EMOS Twitter. The Twitter handle is @EU_EMOS. It is now time to start with our webinar. Before I give the floor to our speakers, let me first explain how we run the webinar today. As you can see, the EMOS webinar stream on Zoom. The webinar is recorded, and the recording will be uploaded on the EMOS YouTube channel, where you can already find the recording of the past webinar, as well as the past 2 EMOS workshops. As participant, you can watch and listen to the webinar. You can also use the Q&A manager to pose your question to the presenter during the webinar. Our speakers will be answering questions on 3 occasions during today's webinar. 2 times during the speech and 1 as part of the final discussion. Should you have any technical problem or question, please send a message in the chat. You will be contacted by one of the members of the technical staff. Today, I have the pleasure to host Johannes Gussenbauer and Alexander Kowarik. They are working at the Unit for Statistical Methods and Survey Methodology at Statistical Austria, the National Statistical Institute of Austria. Alexander Kowarik is the head of this unit. Both of them are senior methodologists with many years of experience. They are active contributors to the R open source community with a focus on official statistical applications. They have been and are currently involved in several European projects on statistical disclosure control and the use of new data sources in the production of official statistics. Within the current project Center of Excellence for Statistical Methods and Tools, they are responsible to further develop, maintain, and document their SCD tools. Today, they will present about statistical disclosure control and synthetic data generation using R. Alexander, the floor is now yours until the first question break.
Thank you very much. We'll just start sharing my screen. I hope that's okay. Yes, okay. So thank you, Francesco. Thank you everyone for joining today. So we will this afternoon guide you through statistical disclosure control, a bit on the methods and a bit on the R implementation, and also on the synthetic data generation with one of our R packages, SimPop, that will be the part of Johannes after my presentation at the beginning. So we will have a short kind of motivation or introduction about STC methods in comparison to synthetic data generation. Then we will talk about microdata protection. Then actually I forget that in the overview. Then there's the synthetic data generation part, and then there's only once the STC for tabular data, anonymization of tabular data. So the last 2 bullet points are the same. So going immediately into the motivation. We have prepared a short poll on this slide. So some of you might recognize this person, and the first poll is about just a text field where you can enter the name of the person you think that this picture is kind of the original of this picture is taken from. Stefan, could you? Right, it's already there. So just type in, if you have any idea who this person is, type in a name. You can also type whatever, like don't know or unknown into the response field. That's also fine. I think we were like 30 something, 32 participants. It's listed here as well. So we just wait a few seconds until everybody had the chance to make his reply to the poll. So it says in the subtitle, it's a synthetic picture, but it's based, of course, on someone. And that's kind of the question, who the original person was. We have 20 replies. I think it's slowing down. '22. So let's see what the results are. I'm actually not totally sure how I see it. Do I have to stop sharing? Maybe I have to stop sharing. I tried it. Share results. Okay, I don't really get it. I'm not used to pause and Zoom. But I think we move on and don't.
Okay. Okay.
And you still see my slides, right?
Go, yeah, we can go on because.
And you still see my slides. Is that correct?
Yeah, we can see your slides. Yeah.
Okay. So anyway, so there was basically the same question for this picture, which is kind of a stylized way of STC applied. So obviously, normally we apply STC to data and not to pictures, but that is kind of we do some recoding. So we change the resolution and we do some local suppression. So that's the black bar. So that did not work, but that's the pictures again. So the original photo is on the left. So that's the official presidential portrait of Barack Obama. And I took these examples from Twitter, and they were actually for something else. So there was this generative AI algorithm who kind of zoomed out of a picture. So you gave it a picture with very low detail, like the one in the middle, and then it zoomed out to increase the details with that. And the first result the algorithm came up with is the right picture, which obviously is not even close to how Obama actually looks. Then there was some discussion in the Twitter feed, and then they tweaked it, and then they came up with the second picture on the right. And so to motivate the difference, or what the difference or similarities between STC and synthetic data could be. So STC is kind of this middle picture. So you kind of remove detail from the picture, and then you judge, is there still too much risk to disclose, to disseminate this data set, or is it fine? And then you say, okay, it's not fine yet, and we have to do it, like apply another STC method, and this method could be like this black bar, like local suppression. And with synthetic data, you have other problems. You generate a synthetic data version, and the first version you generate, okay, it's basically also a person and also a face, but not a person of color, and also not resembling Obama in the other way, except maybe the shape of the face. Then you tweak it. So obviously there's a problem of kind of bias in the synthetic data generation, and it's also you promise a lot of detail with synthetic data, and that promise might not actually be like true, or the details might not be correct at the end. So it's still a lot of a trade-off in both worlds, let's say in the STC methods or in the synthetic data generation, between kind of protection, so limiting risk and utility. And that's the kind of the general topic in STC. You want to minimize risk, and at the same time keep as much information, so keep the utility high, or the other way around, keep information loss to a minimum as well. And I mean, the background of this is that they used the zoomed out versions of the picture to train the model, and from a far away, they look the same. It's just another way of looking at it, except of course the picture with the black bar. And that's another thing. So synthetic data on a high level might resemble closely the original data, but if you go into details, they might be quite different. So comparing them more strategically or more systematically, both, as I said, want to reduce risk and maximize utility of the data. Both methods, let's say, are more complicated for hierarchical data. So for example, if you have households in the data set, which we often have, think of a census-like data set, then you have a household structure and then persons in the households, or you might even have more hierarchical levels. You might have a building identifier, then you have like the households within a building and persons within households. So that's definitely adding a level of complexity to the problem. And at the end, both they will not end up with a re-identification risk of 0, because even the first picture I showed you, if you knew the portrait of Obama beforehand, you might have guessed that that's the person behind it. So with STC in general, it's a loss of granularity. So you cannot provide the same level of detail as the original data or the synthetic data, and it's at least traditionally in an individual approach or a manual approach for each data set. For synthetic data, the pros are that you can provide a high granularity, but it's still a complex generation process. The re-identification risk is not 0, and also harder to assess. There's like attribute disclosure that can still happen, and there's membership inference. So that's also still a problem in the data. Okay, with that short introduction on the why we look at both STC and synthetic data, I will go a little bit into microdata protection methods and how we do that, or how it is implemented in R. There is an R package called STC Micro. It's the official version is on CRUN, and the development version is on GitHub, as well as the issue tracking is on GitHub, as it's normally the case. It's a collaborative development with colleagues from Statistics Austria, but also many other institutes. And there's a European project supporting the R packages, which was shortly mentioned by Francesco in the introduction. So it's now an official ESS tool for STC, one of the official STC tools. What are the methods that can be used? There are methods that are for categorical variables. The first thing is risk estimation, or the first thing, if you want to assess if you can publish a data set, you have to estimate the risk. The main concept is still k-anonymity. So the k-anonymity is just using the frequency of the combinations of certain key variables. So you define a set of key variables that are well known to a possible attacker of the data set. So somebody who wants to identify a specific person in the data set. These are the key variables, and then you compute the frequencies of the cross-tabulation of these key variables, and k-anonymity is then just setting a certain level. So how high the frequency has to be so that it's okay with your k-anonymity rule. There are also other disclosure risk estimation methods implemented in the package that you can use. Then there are methods to actually perform protection. There can be divided into non-perturbative protection methods and perturbative protection methods. So the quite easy one is top and bottom coding. So removing values, the highest values and or the lowest values from the data. Recoding, so that's kind of the image I showed you. So changing the categorical variables by removing or like a certain level of detail. For example, if you have like some classification, a nice classification by going one level up, so going from like 3 digits to 2 digits, for example, or by merging certain classes, ideally the ones with low frequencies. And perturbative protection methods are like swapping or post-randomization, so where you actually change the values observed in the categorical data. So you keep the level of detail in the categorical data, but you change the values. Then there are also, of course, numerical variables in your data set and a set of methods for them. The top and bottom coding again, microaggregation. You could also use microaggregation, of course, for categorical variables. This means that you define somehow a similarity measure, like a distance function, and then you combine these observations. So, for example, like you take a k equals 4, then you take the four observations that are similar and take the average of the income, for example, of those 4 individuals, and then all these 4 individuals will have the same income. You can do rounding. I mean, of course, if you think about like an income variable and you report it up to the cent, then it's very specific, very unique. But if you round it to like 100 euros, then it's not that unique anymore. You can add noise to numerical variables, and again you can just do swapping, rank swapping, or there's also something called shuffling, where you also change values from these variables with other observations. In R, we implemented that with so-called S4 class system, where we have a class called STC micro object with some slots, and where specific information is going into. So you have the original data of, obviously, then you have the names of the first thing is this many key variables is the modified key variables. So all these methods only change the variables you define as key variables, either the categorical or the numerical key variables. And in this manip key vars and manip num vars, you will have the modified key variables. Then the next two slots, the categorical key variables and the numerical key variables, is just the names of the variable you have defined. And the computed disclosure risk is in its own slot. It's like a list object with several computed risks in it. And it's updating automatically if you apply methods to it. And these are some methods, for example, so you can add noise. So you always call the method on a predefined STC micro object. You can add noise to the numerical key variables. You can apply the pram to the post memorization. You have a rank swap method for the rank swapping, a shuffle for the shuffling method. So that's basically all the methods in the package correspond, like methods in a methodological sense correspond to methods in a computer science sense. What's interesting, or what's nice to use, is also there are nice tools to generate a report. So just by calling the report method on your object, you can generate a report about the anonymization process. So summarizing that, there's like an internal version and an external version. So the internal is for basically to be used just by you who also knows the original data, and the external version can be shared with the scientists, for example, who are using your data set afterwards. And you can always go one step back. You don't have to start at the beginning. You can just undo last, and it will go one step back in your anonymization process. So cancel out the last applied method. So a small example could look like this. You have a function to create an STC object where you plug in your data, you define your key variables, your categorical key variables, your numerical key variables, and sampling weight in case of the data being a survey. Then you can immediately look at the risk object. So it's at this point in time, it's 1, so it's 100%. So that's a high risk, obviously. Then we can apply some methods and automatically, so we apply the add noise, or we add noise to the data, and then we look at the risk again and see that it went down dramatically. So it's a small example of one STC approach. There's also an STC micro GUI and STC app, so you can do most of the methods from this GUI. So you load the data set in the GUI, and then you define the different setup options for your anonymization problem. There's like a microdata viewer. You can change the variables to be in the correct format within the GUI. And then in the anonymization tab, you can apply anonymization methods to your data. So at the left side, you see that you can just select one of the methods, and then you have the parameters for the corresponding methods. And you always have a summary that is updated after you apply the method on the specific variables you have defined. There's also the risk utility in the GUI, so you see the different risk measures. You can browse through them. There's some visualizations for the information loss. And what's also really nice is that it's reproducible. So everything you clicked you can export as a script. So that's the next time you get a new version of the data set, or like the next wave of the surveys coming in, you can just reuse the script and apply exactly the same methods. There's one method that is not yet included in the GUI, and at the moment there's not a concrete time frame when it will be included. That is target record swapping. That method was developed within an ESS, a European project, and it's the recommended methodology for the sensors. And it's a data swapping technique applied on the microdata. And so basically households are swapped between regions, and then you have to use the swapped microdata for all the outputs you're producing. So that's your data set for all the publications is then the swapped microdata sets, and that's applied by several countries to the current 2021 census round. And it's targeted, so it's called target record swapping, and the targeting means that you target high risk individuals with the swapping, so they have a higher probability of being swapped. And the k-anonymity is used to compute the risks, and you can also provide your own risks if you want to use a different risk computation method. And the swapping between the households is based on, we call them similarity variables. So ideally, you swap not just like a risk household with any random household from another region. You swap it with a similar household. And for that, for example, you want to have exactly a household with the same household size, so you don't change the total number of persons with that setup. I won't go into detail about the setup or what you have to call to get the record swapping started. There's the things I mentioned is in the parameter setup as well. So you need a geographic hierarchy and the other variables in your data set, so you can call the target record swapping function. It's called record swap, the R function. With that, I stop sharing and hand over to Francesco shortly.
Thanks, Alessandro. I cannot see any question now. Maybe we can go in the part of Johannes, and then we have question at the end. Oh, maybe there is one, maybe. Yeah. Can you explain how display risk works again?
So I have not shared my screen anymore, right? Yeah. So in the graphical user interface, you can there's just a where is it here? You can just go to the corresponding tab in the Shiny app, and then the risk is displayed automatically. And also within so that's the graphical way of accessing it. And from this short example, if you want to access it directly, there's just a slot risk in the STC object, which is updated and computed automatically. So all you have to do is create the STC problem, and then you can access the risk either in the command line through the slot or through the GUI by going to the risk utility tab.
Okay, thanks. Maybe we can go on with Johannes.
Yeah.
Thanks.
Yeah. Thank you. Okay, yeah. Thank you and hello. I will continue with the topic on disclosure control and to be more precise, talk a little bit about synthetic data generation with R, specifically with the SimPop R package, which is also on CRAN. And I will cover these three topics mostly in my talk. So quick introduction to SimPop, how can we use the basic functionalities of it, and also at the last point coming a little bit to a calibration of synthetic population, which is also part of the SimPop package. So the SimPop package is specifically designed to generate synthetic microdata, and more specifically really like household kind of data. So Alex said in his talk, census-like data. So we have households in different households, and in each household there is a number of people living there, and households can have different locations on a map, and people living in households can have different attributes, and this should ideally also make sense when doing the synthetic data generation. So for instance, you wouldn't like to have a synthetic household with only children in there, because it would be unrealistic, and it would be easily identified as being like a badly generated household. And why would we want to generate synthetic data in the first place? Microdata becomes more and more needed also by scientific community and the public. So it's like the more detail you can get, the better it is. But you do have a lot of also legal difficulties protecting the data, and this makes it difficult to disseminate basically. And there are ways to get more detailed data, but this can take really long time. So this could, in some cases, also take months to get access to specific scientific use file microdata from Eurostat, for example. So then it would be nice to have this synthetic microdata, which you can easily distribute, where you do not have this legal issues or this difficulties disseminating, because the data is synthetic anyways. So what should the synthetic data be? So how should it be set up? It should not reveal sensitive information. So ideally you are we're at the same had the same concept with applying more standard SDC tools, where you say want to protect individuals. You don't want to just copy the data basically. That wouldn't be so nice. And you want to preserve a certain kind of structure in the data. So it shouldn't be completely nonsense, but it should resemble the structure of the original data, but in the same time not be just a copy or not reveal individual data. So what can the synthetic data be used for? Usually it's prototype development and microsimulation. Those are, I think, the most already in working examples, basically. From what we hear, or what we have experienced in the synthetic data world, is that there is a lot of promise when using generative synthetic methods. But I think, as Alex has shown before, there are some drawbacks on like what how has the data really changed, and how good is the utility really. So you need to keep it a little bit in mind that although you can do a synthetic data generation, it's not like as high of a quality, or can't expect it to be as high of a quality like the original data. This kind of outlines the workflow that you can operate on with the SimPop. I will mostly focus on the generation part. So the orange-yellow part here, which is generating the synthetic data. Before, there's also utility functions in the SimPop where you can actually adjust your inputs for the households or for the synthetic data generation. So as I said before, we are now really specifically talking about generating some kind of census-like data. You can also do this with other kind of data using the SimPop package, but this is where it has been initially designed for. And now it comes from R script, so you usually have to in R load your libraries, and then you can load this data set. This is a data set from the SimPop, and then you have the first function that we have to apply, specify input. This kind of starts the procedure where we specify the input. We say we have some data, we have a household identifier, which is optional, a household size also optional. This is a weighted sample, so we can specify weights. We can also say how it has been drawn. So there's a stratification variable that we can specify, and there's also some other variables here. And then we start to initialize from our specified inputs. So this will create some kind of objects. We can then say, okay, from this object now, I want to generate structure. And here we can do sampling, or we can do it directly. And there are also other methods how we can kind of start off with just starting with a few basic variables that are generated. And then the idea is to then add variable by variable. So in our example, we will start with age, and this is the variable is actually the gender. So we have age and sex here. And those are the two variables that we will start off, and then we will try to add variable by variable, and those can be categorical or continuous variables. And for each of them, there is one function. So we have sim categorical, then we want to have a different additional categorical variable. So I say I want to have in addition other variables, which are here categorical. And there are a number of different methods that you can call with this package. So you have from XGBoost to multinomial distribution. You have also, these are the Ranger and the C-Forest. Those are random forest implementations. So those are all functionalities from different other R packages, but we made use of them in our package to synthesize categorical variables, and the same for continuous variables. So there's also different kind of methods here. Maybe you can see that there's also a multinom method here, although this is usually used for categorical variables. But in our case here, when we want to maybe predict the income, we can also use this multinom method, and then it will try to predict income brackets and then draw from the sample that we started from the same income brackets that are in the sample for the synthetic population. So this is how this is used, and there are kind of a lot of very specific models implemented here where you can really tune it. But it's important that you really do tune it. So this is not a method or a package where you can just type in one or two functions and then the data will be perfectly synthesized. You should take care of how do I want to model the data, what kind of model do I want to choose, what kind of parameters are useful. So you do have to make these choices, and this is on purpose, basically. So we do believe that making these choices really is the right way, and there's not really a good automatic procedure to just generate it blindly and then hope for the best. So there's also some additional other modeling functions. You can also take into account, this is very specific for census-like data, relationship between household members. So this is a different data set from the examples in the R package SimPop, which you call sim relation is called the function. And then I can take into a relationship for the synthesizing that there is some kind of household structure there and how individuals relate to each other, and this will be taken into account while modeling. And I can also do components when it comes to that I have a total, which is net income, for instance, and this is made up of different income components, for example. Then there's also possibilities built in how I could model this such that all these totals, all these sub parts sum up to the total for each household or for each individual. So those are more like nice to have functions. Should I go to the questions now, or should we ask them later?
Yeah, you can go with the question if you think can be fine.
Okay, I go from the first one. I'm not sure, slide 16. I think that is from the previous. I think that's from the previous from your talk, Alex.
Yeah, I think that for you is for sure the third one. Why should I use multinomial distribution in that case? I think refer to slide 7.
Yeah, I think I maybe have answered it already. So the how this is implemented for the multinomial distribution. I think for the continuous case, that's what the question is relating to. If I believe that's correct. Then how this is implemented here is that you can define income brackets, and then you have kind of income categories. You predict those, and then you draw from your input data from the sample or from whatever kind of input data you have. You then draw from the same income brackets for your synthetic population the values. So that kind of helps also to better get a handle on the low and upper tails, specifically for stuff like income, which is kind of difficult to get correct. The upper and lower tails they're kind of tricky. Do we share?
Okay, there is another.
Yep.
There is another one that is, what is the sim population object actually?
The simpop object actually is also an S4 object. This is also an S4 object, and it stores the data that you started with, the kind of parameters that you started with, and there is another slot which holds the synthetic data, basically. So.
Okay, maybe you can go on, and then we answer the others at the end. Okay.
Okay, I'll just go on.
Thank you.
So there's other kind of nice to have features there. Also, something that could be nice is if you want to introduce a more granular kind of geographic resolution to your data, then we have a init spatial function for this. If you have something where your input has a so-called age heaping, so we had this in some of our projects where you have census like data, and age heaping means that you have kind of peaks at multitudes of 5. So there's a lot of 5-year-olds and 10-year-olds and 15-year-olds, and those are obviously faulty inputs. So you have kind of these functions to correct your inputs and start better off, basically. And when you have everything synthesized, there's also the possibility to calibrate your synthetic population. So you can even have a better fit to some distributions. Maybe the sample you start with is not calibrated to these distributions. Maybe you want to get really sure for some distributions that you kind of match targets exactly, because if you do desynthesizing, you can kind of might not touch it extremely well, all the target distributions, and then you can kind of supply a table. So this is where we say, okay, we want to build a table here in the first lines. So this is a table. This should be kind of like nuts2, sex, and something else, and then and citizenship. So we have nuts2 region, nuts2, sex, and citizenships, and then we want to kind of make our population data or synthetic data fit even more precisely to these distribution. So what's the idea behind this and how do we do this? Basically, the idea is that we now have our synthetic data, and then we kind of want to select and deselect our individuals such that we can reach the target populations. And this is not easily done, basically, because we have this kind of dwellings and people living in dwellings or household situations. So if I would pick any person from this chart now, so I have this chart, and each people in a smaller circle, they live in a household. So if I take any of the yellow ones, so for instance, the one in the top left, then I get 2 black ones also, and they will have different attributes, these people. So maybe my target distribution is about some people, and by choosing only households, it makes it difficult to get a correct distribution when my distribution that I want to fit on is only on persons. And it could also be that you have different target margins where you don't have the overall distributions, but only one part of it, basically. And then it also gets kind of tricky. So this then results in kind of an optimization problem where you want to try to find the best combination of people where which fulfill all your target margins. And there we have implemented this simulated annealing procedure in the SimPop. So basically, you start with a synthetic population, which is fairly large. So a simple step would be kind of like, okay, you duplicate it once or twice. And then you do this selection and deselection using the simulated annealing until you reach your target distribution, basically. So this is really in very simple terms. So this is the function for it. You have this CalipPop, it's called, and there you put in your SimPop object, and then you can have these tables where you say, okay, I have some tables on a personal level or on a household level, and there are some distributions here that I want to fit. And then it will try to find a solution, or it will try to find the best solution that it can to fit these. And here's some math for it. So this would be our objective function, which kind of says, I want to have very little difference to my target population, to my target margins. I want to have very little differences here. And here there is a sampling probability, just meaning that if I have kind of like too many households in a region or too many people in an age group selected, then I want to kind of target these and want to specifically deselect them with a high probability and switch them to another group of households or to another group of people, basically, so that my target population is reached. And here's just some motivation. So how can we do this? This is from a toy data set where we started. The red bars are the synthetic data before calibration, and the black bar here is what I want to achieve. And with the epsilons, I go lower and lower. So I can see that with the purple bars, I'm really very close already. So I can't really see a difference between the purple bars and the black bars in any of the facets here. So you can, in some cases, can get really close to your target, and that also adds kind of a value to your synthetic data. So there are some references, and I will try to open again the questions.
Yeah, just
Okay.
maybe we just a couple of them, then we postpone the others at the end. Just the first one is what is the current level of use of this method within Statistical Austria? Do you share synthetic data with external users?
Yeah, maybe Alex can also jump in there? I think
so we don't do that on a wide scale. There's like, at least for EU Silk, so there's so when income and living condition, there's a public use file for several European countries generated with SimPop. And there were some occasions where we used it, but it's not used on a wide scale for general purpose synthetic data sets we share with external users.
Okay, just other two that are very specific, and then slide 14. Could I use Monte Carlo techniques instead of multiplying my population and use objecting functions? Slide 14.
I think that is relating to the simulated.
Yeah. I'm not sure.
Or maybe if you want, you can answer by a written answer. It's maybe asking some more clarification about this question, and we can go with the last part of the webinar now. Do you agree?
Okay.
Okay. Okay.
I will stop
Alex.
sharing.
Yeah.
Again.
Thank you, Johannes. Yes.
Thank you. So the last part on the anonymization of tabular data was prepared by Bernhard Meinl, who cannot be here today. So I will present on his behalf. Given the time constraints, I will concentrate on the high-level view, and will not go into detail later on the R code. So I think it's quite obvious to anyone that, I mean, if you share microdata, then you have to do some effort to provide anonymized microdata, but it's not that obvious that the same thing is true also for tabular data. So there is disclosure risk, or there can be disclosure risk for aggregated tabular data that you disseminate or share with someone. And the goal of statistical disclosure is again the same as for microdata, to protect the statistical units that contributed to the table. And again, it's a trade-off between risk and utility. So we have frequency tables and magnitude tables. So frequency tables, they are just counts of units in it, and magnitude tables, there you have like a turnover or some other variables by some marginal variables in a table. So let's start with like an easy example. You have like a female and male table, and for some groups, so the example is there's only one female that is single, and then if you add a third variable, so you have a table of gender, marital status, and income, and the only female is in one marital status, and so in the single status, then you can derive the income group for this person if you know the other two variables. So that's kind of the disclosure risk, the problem from such populations. And then there's another issue or complexity to the problem, that there are linked tables, so that identical cells will not just appear in one table, but will appear in multiple tables. So for specifically for this problem, there has been software around for quite some time. So Tau Argus is the most prominent one, and in line with the methodology applied in Tau Argus, the R package STC table was developed, and several packages around it that we can also apply this methodology. So I will shortly mention 5 R packages: STC hierarchies, which is kind of the backend to set up hierarchies in R for the use in Statistical and cell key. Then Statistical is doing the suppression of tables, hierarchical tables and linked tables. Cell key is supplying the cell key method. I will talk about that in a second, and then just a mention of what you can do for spatial data. I will go forward into this slide. So most of our tables are generated according to some classification variables. Think about like NACE, so economic activity, or also like education, or just like geography. We have seen it for target record swapping. They also have a hierarchy from like national level to states to like municipality. So there's a hierarchy that is connecting the different levels, and for kind of saving or processing this kind of hierarchical variables, the STC hierarchies package is used and important. So it's kind of the backend for STC table. And you can then, if you have set up this object, this hierarchical object, you can also query it. And the package that is actually protecting the statistical tables is STC table. And what you can do with the package is you first set up a complex statistical table setup that you want to protect. You define how to identify the primary sensitive table cells, and then you protect the sensitive cells with with different algorithms by secondary cell suppression. And there's also a link or an interface for Tau Argus, so you can export a problem instance in a so-called patch file, and then you can process it with Tau Argus and import the output of Tau Argus again in the R environment. So the code, just shortly, there's a STC test problem. If you just want to look at to play around with it, there's a function to generate that with just a few variables, just region and gender in it, and the frequency. You can export the problem as a data frame, so to have a nicer or easier to export format of the problem. So you have a flat version of the problem, basically. And then for the primary suppression, I mentioned that you have to define how you identify primary sensitive cells. One often used rule is the frequency-based, like k-anonymity explained before. You set some n, which is sufficient for the cell to be safe. The cells not satisfying the rule will be marked as unsafe, and there's also the like X for secondary suppression in the table. So that if you then apply a protection method, cell protection methods, you will have the same table as before, but you will have like an STC status for each cell. So S means safe, U means unsafe, so it's primary suppressed, and X means it's secondary suppressed by the protection algorithm. So that was very fast, the STC table package and the approach for tabular suppression. So keep in mind, maybe as an extra comment, that if you add more level of detail to your dissemination tables, you might end up with having to secondary suppress at a higher level which was fine before, just so you have enough secondary suppressions to protect your primary suppressed cells. Another approach than suppression is perturbation. So the persistent perturbation of statistical tables can be done with cell key. And what the algorithm implements is an perturbation based on so-called record keys and cell keys. They make sure that every time the same cell occurs in different tables, that you make the same perturbation for this cell. And this is done via lookup tables. So for a specific cell record, you have specific value in the lookup tables. And to generate those lookup tables, there's this P table for perturbation table package. And there you kind of define the risk parameters for setting up the problem. And yeah, I mean, that's especially useful for large and linked tables or cubes, because then you would end up with if they provide a high level of detail, then you would end up with a very high number of suppressed cells, and you can avoid that with this perturbation algorithm. The main drawback is that you lose additivity. So that's can be a problem in communicating the results, especially. And again, you set up the problem in a similar way as you have to do for the STC table package. You define each dimension of your table with a hierarchy object. X is the input data. You can generate the record keys automatically. Here it's just define it how long they should be, and you can have a sampling weight if it's a sample. From P table you define you get the parameters for the perturbation table, and here it's just called with the defaults. And then you can extract the perturbed table and look at it. At the bottom you see the table how it is after perturbation. So it includes the dimensions of the table, and it includes the perturbed and unperturbed, weighted and non-weighted. So UVWC is unweighted count, and WC is the weighted count, and with the P in front of the two, that's the perturbed corresponding value. Just to mention it here, there's of course another aspect that we now publish a lot of data with geolocations. So for example, raster data, and for that there's a package by Edwin de Jong from Statistics Netherlands for STC Spatial, where you can apply multiple algorithms to this raster data, such as smoothing or aggregation. That was my last slide. Here, just I have one more slide I use in a lot of presentations. If you are working in official statistics or are interested in the software behind it, there's an awesome official statistics software list on GitHub. A lot of us from the official statistics world have kind of contributed to a list, or even have contributed software to this field. Thank you.
Okay. Thank you, Alexander, for this very interesting, and also Johannes for this very interesting presentation. we received a lot of questions, and if there are others, please write in the Q&A manager. And just a curiosity for myself, it's a general question that we ask at the end of all the EMOS webinar. Do you have any particular suggestion for the students that approach for the first time to these topics?
I mean, for students, it's to be aware of this, especially. I mean, if you use the data in one of the like safe centers or the research data centers of one of the NSIs or also of other institutes, you probably, if you want to like kind of extract the information, there will be like an output checking at the end. And I think it's important to be aware of this SDC thing in general, that you also can discuss then with the colleagues who are doing the output checking, and may say that this output, this table is not safe to be extracted from the safe environment, for example. So I think it's good to have some basic knowledge about how NSIs treat this data for this from this perspective. But also, if you actually are working in a project that gets microdata, be aware if you publish data or publish tables that there might be a disclosure risk involved.
Okay. Johannes, do you want to add something?
No, I don't have anything to add.
Okay. Okay. So I think we can close the webinar. Thank you, Johannes. Thank you, Alexander, for this very interesting presentation. And many thanks to all our participants who joined us today. As participants, you are invited to fill in a short survey about today's webinar, and the survey will open in your browser just after the end of this Zoom meeting. If you don't have time right now, you will receive a link by mail to fill in the survey later on. We really appreciate your feedback to further improve our webinars. The next webinar is scheduled at the beginning of the next year on January the 17th, when Oriol Bosch-Jover will present on measuring citizens' digital behaviors using web trackers and data donation. For this and future webinars, please keep an eye for our website, emos-event.com. Thank you again for our speakers, and have a nice day.